everyone, welcome back to my channel. So in this video I'll be explaining to you all the ventilator settings and the different modifications we can do for patients with ARDS. So let's get started. Now, the problem with ARDS is that the alveoli are stiff and full of fluid, and the patient cannot maintain ventilation on their own, and so they need help with mechanical ventilation. So you need to know what settings you would set them on. This is an example chest x-ray of a patient with ARDS. They're essentially in a state of pulmonary edema and respiratory failure, meaning they can't maintain oxygenation and ventilation on their own, because their alveoli are full of fluid, they're stiff, and the patient becomes hypoxemic. And without assisted ventilations, they will die. Now, this is how a ventilator works, is that it does the job of pushing in oxygen at a certain pressure, pushing the alveoli open with oxygen to allow gas exchange, and CO2 diffuses out anyway. So every part of this process has a different setting. So how much oxygen are we gonna add? How much pressure to open up these stiff alveoli that do not have surfactant, at what rate, and with what volume? So this is the typical ventilator. How much oxygen would you provide is something called FiO2. Usually inspired oxygen that we breathe from the atmosphere is 21%. However, obviously this 21% would not be enough for someone with respiratory failure. And so typically we provide 100% oxygen for patients with ARDS. Now, PEEP, that is how much pressure you would use to burst open the alveoli. Those stiff, collapsed alveoli, how are you going to open them up? You need to maintain a little bit of pressure at the end of expiration so that they do not all collapse. This is called positive and expiratory pressure. And we like to keep a balance of 5 centimeter water pressure in order to keep them open, but at the same time prevent pneumothorax. We don't want them to be of very high pressure. So this, how much oxygen and how much pressure, determines the oxygenation. Okay, so this should be enough to deliver proper oxygen. Now, how about ventilation? Ventilation means gas exchange, and it's measured by carbon dioxide. And so for that, we're going to use tidal volume and respiratory rate. What does that mean? Minute ventilation, that is how much volume of air goes in and out of your alveoli per minute, equals the volume per breath, called tidal volume, multiplied by the respiratory rate, which is how many times you breathe per minute. So if you get the rate per minute and the volume per breath, you get the minute ventilation. And so if you want to simulate the real ventilation in a normal person, you would do that on the ventilator using a tidal volume of around 400 ml. Or you can calculate it based on the patient's body weight. That's 6 ml per kg of body weight. So let's say someone is like 50 kg, for example, then you would give them 300 ml. Okay. Now, how fast would you give them this volume? That's the respiratory rate, which is typically maintained at 10 to 12 breaths per minute. Okay. So here, this way, we're just setting up the ventilator to simulate the real normal respiration. So how can we actually monitor that? How can we make sure that the patient is responding? As I mentioned earlier, you monitor oxygenation by the settings of FiO2 and PEEP. FiO2 must be 100%, PEEP must be 5 centimeter water. You monitor that by an arterial blood gas showing PaO2, or the oxygen partial pressure in blood. If it's within normal range, which is 80 to 100, that means that your FiO2 is good, your PEEP is good. And we're going to see how to fix it if it doesn't turn out to be normal. Now, ventilation, that is by tidal volume, which should be at 6 ml per kg ideal body weight, and respiratory rate, which is at 14 to 20. Now, how do I monitor that? This is a typical arterial blood gas analysis showing you how to monitor oxygenation by the PaO2, should be 80 to 100 millimeters of mercury, and how to monitor ventilation, that's by PaCO2. Make sure that the patient is not retaining extra carbon dioxide in blood. It should be from 35 to 45 millimeters of mercury, no more, no less. And the pH, you also monitor by that. The more the CO2, the more acidosis. So the lower the pH, and that means that the patient is retaining CO2 and you need to wash out quickly. So in that case, you may want to increase respiratory rates. How do I manage each situation? Let's say the PaO2 turns out to be really high, over 90, and that means the patient is getting more oxygen than they should. In that case, you may want to decrease the FiO2. Instead of breathing 100% oxygen, they can breathe 90%, 80%, or whatever. And let's say the patient is hypoxic still, despite good FiO2 and PEEP at 5, with a PaO2 under 60, that means you need to improve oxygenation. Now, there is no way I can give them oxygen more than 100%. So the only thing I can do is actually to increase the PEEP. That is to keep the alveoli open for a little longer in case they're collapsing. Now, let's say the problem is not in the PaO2 to begin with. It turns out a normal value of, let's say, 85, and everything is cool. Yet, there is a problem with ventilation. That is, the patient is retaining carbon dioxide and they're getting acidotic. In that case, I want to wash out the CO2 by ventilating them faster, by increasing respiratory rate, and as a last resort, increasing the tidal volume. Now, let's say it's the other way around, and in fact, they're washing out more than they should, and the PaCO2 is low with alkalosis. In that case, I'm going to first try to decrease the tidal volume, then decrease the respiratory rate as a second option to kind of retain a little bit more CO2, and if that doesn't work, still the last resort would be to increase sedation. That means that I'm decreasing the central respiratory stimulation. I hope this video helped, guys, and let me know what you think. All the best.